Okay, so now we're going to do Newton's second law part 2. This is what do you do with a problem where all the forces are not in exactly x and y directions. So I've got a person trying to pull a heavy box across a frictionless floor. They're pulling with a force Fp. And I want to know what is the acceleration of the box. Okay, so step number 1 was the free body diagrams. Now luckily for this one we only have one object, so we're only going to need one diagram. Okay, so here's my object. It has a mass of m. I'm not giving you numbers. We're going to do this as, well, as generally as we can. Then I've got this force. It's at an angle, Fp, and it is at an angle of theta from the horizontal. Okay, I don't really know what theta is. Well, if I was doing this for a real problem, I'd give you theta. Okay. We also have gravity, because that's always around. We can't get rid of that. Force of gravity, that's m times g. And I also have the normal force. Because this is sitting on a floor, the floor must be, the box must be pushing into the floor, so the floor must be pushing back on the box. I don't really know how much that is, though. I will tell you, I know it's not the same as gravity, for sure. Okay, so that's my normal force. Come on. Again, I don't know what the normal force is. I'm just going to leave it for now. Okay. So, second step. Newton's second law. Or, sorry, no. What do you call it? Net force. Now, this time, I have more than one dimension. So I actually have to do net force for each dimension separately. So, the net force in the x direction, well, this is not an x at all. Neither is this. The only thing that is an x at all is this green one, the force of the pull, but it's not completely in x. It's kind of partially. That means I need to find the x component of the pull of the force. Okay? Now we already know how to do that from last unit. If I want this component, that's adjacent to the angle, so I'm going to do the hypotenuse, Fp, times the cosine of that angle. So what I get is Fp cosine theta. And that's it. And it's to the right, so that's positive. Then I also need to do net force in the y direction. This one has a little bit more to it. In fact, I'm going to run out of room here. For one thing, I do have something straight up, Fn, so I'm going to leave that, Fn, straight up. I also have Fp is kind of pointing up, but I'm only going to be able to use the part in the y direction. Oops, come on. So that's the sine. So I'm going to do plus Fp sine of theta. And then I've got this pointing down, so that will be minus mg. Okay, so that's my net force stuff. Third step, Newton's second law. Now, I have to do Newton's second law in x and y as well. I'm going to actually do y first because it's a little bit well, no, let's do x first. Okay, so I know that F net in the x direction equals mass times acceleration. Right. So F net in the x direction was F, oops, ooh, that was weird. No, it's not. I do that all the time, actually. Fp cosine theta equals, mass is m, so I leave it like that, and then a. Now, if this was a real typical problem, I would already have, I would have Fp, I would have theta. So to get a by itself, just divide by m, and I get that the acceleration, and that's, by the way, in the x direction, is FP cosine theta over m. I actually can stop there. That would be the end of it. Unless I wanted to know, let's say, what if I asked this question, what is the normal force? If I wanted to know what the normal force was, you know what, let's just add that. Let's add that to the question. What's the normal force? I would need to do the y stuff over here. Okay, so F net in the y direction equals m times a in the y direction. F net in the y direction is all this stuff, for normal force plus Fp sine theta minus mg. That whole thing is going to equal m times ay in the y direction. Now here's the thing. If this box is on the floor, and I stipulate that the box remains on the floor, that means that the box does not accelerate in the y direction, because it's stationary in the y direction, it stays stationary in the y direction, therefore the motion does not change in the y direction, therefore acceleration in the y direction is 0. So I can make this 0 right here. So what I end up getting is the normal force plus the pulling force sine theta minus mg equals 0. So if I wanted to solve for the normal force, I would just move everything to the other side, and that's all known stuff. So the normal force would equal mg minus fp sine theta, all of which I know, so I could get a number for this. So this is a typical, probably the simplest two-dimensional normal Newton's second law problem that there is. We'll do another one that's a little more complicated next.